All right, guys. So this video is it's probably going to be a couple videos. The next two videos are to get us into 6-1 and 6-2 uh, in in Unit 6, and it's going to push into 6 dash. It's going to push into Electro 2, so 6-3, 6-4, 6-5. So this is going to kind of give you the intro to Unit 6 and how a bunch of things are going to tie into each other. So, Unit 6, we get into thermodynamics. Now, we already know a little bit about thermo. All right. So, what we know about thermo already, we know the delta H part, the enthalpy change part of thermo, the heat change part of thermodynamics. So, what do we need to know about thermo coming in to this unit? We need to know how to do answer calorimetry questions, calculating the delta H of a reaction given calorimetry data, knowing that a negative delta H means exothermic heat is a product, a positive delta H means endothermic heat is a reactant. A negative delta H means the product's bonds are stronger. A positive delta H means the reactant's bonds are stronger. We need to know that if you have an endothermic reaction, so a positive delta H, that if you increase the heat, that's going to shift the reaction to the right towards the products, increasing the favorability of the reaction. So making a connection between endothermic and exothermic, so positive delta H, negative delta H, and the equilibrium constant. So knowing that for an endothermic reaction, if you heat it up, the reaction becomes more favored in the forward direction, so K increases, the equilibrium constant increases. Or knowing that if you have an exothermic reaction, if you heat it up, you're decreasing the favorability of the forward reaction. That means you're increasing the favorability of the reverse reaction, and that means KEQ for an exothermic reaction would decrease as temperature increased. Okay, and then going into favorability, if I ask you if it's just yes or no, is this reaction thermodynamically favored or not at this temperature? Right now, the only way you know how to answer that question is if you know the equilibrium constant value. So if the equilibrium constant value is greater than 1 at that temperature, you know it is thermodynamically favored. If KEQ is less than 1, then you know that the reaction is not thermodynamically favored. So what we're going to get into in thermodynamics, the new thing we're going to add to thermodynamics is something called delta S, which is entropy change, entropy, entropy. That's delta S, change in entropy, and delta G, which is change in free energy. It's called Gibbs free energy. That's why it's a G, but delta G is change in free energy. And what you're going to take from delta G is now that's another value that will tell you if a reaction is thermodynamically favored or not at a given temperature. And for delta G, you just care if it's positive or negative. A negative delta G is thermodynamically favored. A positive delta G is not thermodynamically favored. So now make the connection between delta G and equilibrium. If KEQ is greater than 1, then you know that delta G is less than 0. It's negative because a greater than 1 value of equilibrium constant means thermodynamically favored, which means a negative delta G. Okay, and they kind of go hand in hand. As delta G decreases, K increases. So the more negative the delta G, the higher the value of KEQ is greater than 1. Okay, well, if KEQ is less than 1, then now you know that delta G is positive. Or if delta G is positive, you know KEQ is less than 1. A positive delta G means not thermodynamically favored. A KEQ value less than 1 means not thermodynamically favored. So I'm going to get into kind of all this, but I just want you to be able to make connections. And so what we're going to do is I'm going to just show you a couple intro things, and then I'm going to walk through all of the 6-1 and 6-2 Schoology assessment. which essentially is just making connections between things. If you know this about delta H, then you know that about delta S, then you know this about delta G, then you know that about KEQ, all this stuff. Making those connections, that's going to be the biggest part of it. Now, there's calculations you can do, right? Just like with delta H, if you want to calculate the delta H of a reaction, you can do delta H of formation of the products minus the delta H of formation of the reactants. If you want to calculate delta G, one way to do it is do delta G of the products minus delta G of the reactants, if you have those values. If you want to calculate delta S for a reaction, delta S of the products minus delta S of the reactants, that'll give you delta S. But really, it's not necessarily about calculating. Yeah, you might have to calculate a value here and there, but it's really what that value tells you about the reaction at that temperature. Is it spontaneous, which means thermodynamically favored, or is it not? Okay, so we want to kind of make all these connections. All right, so before you go into that Schoology assessment, and I'm going to walk you through it, so you can just watch the video and see all the correct answers. But before you do that Schoology assessment, you want to look over the thermodynamic cheat sheet and the notes that tie equilibrium constant, delta G, and cell potential, which is called E cell together, which is an electrochemistry thing. All right, so let me just show you what they look like, and let me explain a little bit more. And again, I'm probably not going to get it through the entire assessment on this video, so I'll continue it in the next one. All right, so let's do that. All right, so again, what you want to look at is thermodynamic cheat sheet. So it tells you kind of the definition of what H is, enthalpy, S, entropy, G, free energy. Okay, but remember, you put a delta in front of it. It's, change in enthalpy. Delta S is change in entropy. Delta G is change in free energy. Okay, so things to know about these things. Positive delta H, we know that means endothermic. Heat is a reactant. Negative delta H, exothermic. Heat is a product. What does delta S tell us? Well, delta S is the change in entropy, which is the change in randomness or disorder. So if the products are more random than the reactants, more disordered than the reactants, that would be a positive delta S. You have an increase in randomness. And if you have a negative delta S, you have a decrease in randomness. That would mean the products are more ordered than the reactants. Okay. For delta G, it's free energy change, and really all you want to know is, well, if you have a negative delta G, that means the reaction is spontaneous. If you have a positive delta G, that means the reaction is not spontaneous. Now, this is an equation that's on your formula sheet. Delta G equals delta H minus T delta S. So one way to calculate delta G is to get a delta H value, get your delta S value, and plug in the temperature here. It's got to be in the Kelvin scale, and solve for delta G. And again, if delta G comes out to be negative, you know the reaction is thermodynamically favored at that temperature. If delta G comes out to be positive, that means the forward reaction is not thermodynamically favored. That means the reverse reaction would be thermodynamically favored. And if it comes out to be equal to 0, then at that temperature, both the forward and the reverse process are equally favored. Okay. Now here is kind of a chart that goes in with this equation. So if you read this equation, and you know that temperature can never be negative because it's on the Kelvin scale, then if this is your combination of delta H and delta S, if you have a negative delta H and a positive delta S, no matter what numbers you plug in here, delta G will always come out to be negative. So if you have an exothermic reaction that also increases in randomness, that reaction will always be thermodynamically favored. It will always have a negative delta G. And so that means the opposite would be true if you had a positive delta H and a negative delta S, meaning if the reaction was endothermic, required heat, but it decreased randomness or disorder, it got more ordered, then that reaction is never thermodynamically favored, no matter what the temperature is. It has a positive delta G. If you plug in a positive delta H and a negative delta S, no matter what the numbers are that you plug in to this equation, you will always come up with a positive delta G. Okay, so when are the sometimes thermodynamically favored, sometimes not thermodynamically favored? That's when you have a negative-negative combination or a positive-positive combination. Okay, So if you have an exothermic reaction that decreases in randomness, that's going to become more favored, or delta G will decrease as temperature decreases. And that should make sense in terms of Le Chatelier's principle. You already know that if you have a negative delta H in exothermic reactions are more favored at lower temperatures. And endothermic reactions are more favored at higher temperatures. So when you have a positive, favorability is going to increase as temperature increases. But think about how that means for delta G. When delta G is negative, the more favorable the reaction is. So if this is your combination, a positive delta H, positive delta S, if that's what you have, delta G is going to decrease as temperature increases. And the way to interpret that, if I tell you delta G is going to decrease as temperature increases, what I'm saying is that the reaction becomes more favored as temperature increases for this combination. Okay. All right. So here is just so this is, knowing if your KEQ is greater than 1, delta G is negative. If KEQ is less than 1, delta G is positive. And if delta G equals 0, KEQ equals 1. Okay, so right now, there are two values that if you know the value of one of these things, you can tell me, is a reaction spontaneous or not? Is a reaction thermodynamically favored or not? And those two values are the equilibrium constant, and you got to know if it's greater than or less than 1, or delta G. But for delta G, you want to know if it's greater than or less than 0. You want to know if it's positive or negative. Okay? But the third value is something called cell potential, and you can get this connection in these notes. Cell potential, which has this symbol E cell right here, delta G and KEQ. All right? So a negative delta G means spontaneous, but a positive cell potential means spontaneous. A positive delta G means non-spontaneous. A negative cell potential means non-spontaneous. Okay? So here's the deal. All right? This is what we need to take. If KEQ is greater than 1, then you know that delta G is negative and cell potential is positive. If KEQ is less than 1, then you know that delta G is positive and cell potential is negative. All right, those are the quick connections you should be able to make. Okay. All right, now we'll learn how to calculate the cell potential. We'll learn how to calculate delta G and all that stuff. But right now it's just, hey, if delta G is this, that means KEQ is this. That means cell potential is this. That means the reaction is this, endothermic, exothermic, entropy change, and all that stuff. All right. So with that kind of just quick introduction of everything, again, you might want to pause the video and read these notes for yourself and then continue the video. Now, I'm just going to go through this Schoology assessment, give you the right answers. So, watch the video and do the assessment, and you'll be good to go. Let's do it. All right. Now, your assessment's going to be in random order. My assessment's not. All right. All right, so let's do this. If delta G is positive, the reaction is nope, I don't have a not thermodynamically favored, so let's go. If delta G is negative, the reaction is thermodynamically favored. So when delta G is positive, the reaction is not, notice the not there, thermodynamically favored. If delta G is positive, the equilibrium constant is less than 1. When delta G is negative, the equilibrium constant is greater than 1. And if you wanted to, you could switch this and this. I could go here, but then I would have to go there. If delta G is negative, the equilibrium constant is greater than 1. If delta G is positive, the equilibrium constant is less than 1. Okay? And again, that means the same thing. Delta G being negative means reaction is thermodynamically favored, and you also know that the equilibrium constant greater than 1, the reaction is thermodynamically favored. All right? Now we're just making the connection between delta G and the equilibrium constant. All right, let's go to the next one. All right. Delta H is the change in heat energy, so thermal energy. Delta S is the change in randomness or disorder or chaos. Delta G is the change in energy, free energy, which is energy available to do work. That's the definition of free energy. Okay. All right, let's keep on going. If a reaction is thermodynamically favored, all right, so we know delta G is negative and equilibrium constant is greater than 1, with a positive enthalpy change. So that means a positive delta H and a positive entropy change. What is the driving favorability factor? Okay, so this is where we kind of have to go back and review something just real quick. So let me pull this up. Okay. Yeah, this is the one I want. All right. So for delta S, the driving force of entropy change is an increase in entropy. So a reaction is entropically favored, meaning favored because of the entropy change when you have a positive delta S. But in nature, cooling down is favored, so losing energy is a driving force of favorability. So when a reaction is favored and it's exothermic, the driving force that's causing it to be favored is the negative delta H. The enthalpy change is the favorable change when it's a negative delta H. But the entropy change is the favorable change when it's a positive delta S. And those are kind of the balancing forces. So if we go back to this question, a positive delta H is not the favored thing in nature. It's the positive delta S that is. So if this is your case, if the reaction's favored with a positive delta H and a positive delta S, the thing that's favoring it is the entropy change. So the process is entropically favored. Now, if you have a negative delta H and a positive delta S, then the reaction is both enthalpically favored and entropically favored. Okay? But for this case, what's the driving force of favorability? The entropy change in this case. Okay? All right. You find out that an increase in pressure favors the products. So that means there's less moles of gas on the product side because an increase in pressure favors the side with less moles of gas. That means that there are more moles of gas on the reactant side. And if there's more moles of gas, you have more moles of gas going to less moles of gas. Less gas particles would mean more order or less disorder. So the delta S would be negative because as the reaction proceeds, you're going from more gas particles to less gas particles. The less gas particles you have, the more ordered your system. The more gas particles you have, the less ordered your system, the more entropy there is. So we're going from more entropy to less entropy, so our delta S is negative. Now, if the reaction is ever going to be spontaneous, then that means delta H, the enthalpy change, has to be negative. Because you can't have a negative positive combo. Let's go back to the chart, right? A negative delta S and a positive delta H is never favored. So whenever you have a negative delta S, the only way the reaction could ever be favored is if you have a negative delta H. So we know the enthalpy change is negative here as well. All right, so let's go to the next one. All right, a reaction takes place and it is found that the reaction vessel gets colder. So that means endothermic, right? Okay, so we know it's endothermic, so that means positive delta H. All right, the reaction's endothermic, so let me put that here, right? Delta H is positive. Where is positive? Heat is required, a reactant. The reverse reaction would be exothermic. The bond energies of the reactants are stronger. So the bond energies of the reactants are greater than the bond energies of the products because energy was absorbed. Okay? So endothermic, K will increase as temperature increases, right? Heat will drive the reaction because heat's a reactant. Increasing heat will drive the reaction to the right, making more products, less reactants at equilibrium, meaning the ratio of products over reactants, which is K, is going to increase. K will decrease as temperature decreases. Thermodynamically favor will increase at higher temperatures. Thermodynamic favorability will decrease at lower temperatures. That's true of any endothermic reaction. The more heat around the system, the more favorable for endothermic. Okay. Delta G will decrease as temperature increases, because remember, it's a negative delta G that means favorable. So the more negative, the more favorable. So if favorability is increasing as temperature increases, that means delta G is decreasing. Okay. And so delta G will increase, right? And remember, cell potential is the opposite. Cell potential will increase, become more positive as temperature, it says temperature decreases, so let me switch that. Watch out for that. And then cell potential will increase as temperature increases. Now remember, whenever you have a positive delta S, the only time delta G can be negative, so which means the only time the reaction can be spontaneous, okay, is if you have a positive delta H. The only way a reaction could ever be spontaneous is if you have a positive delta S. So if you know the reaction is spontaneous and it's endothermic, now you know that the sign delta S must be positive. Okay. Okay. Hopefully that makes sense. Let's go. Okay, blank studies if a reaction will happen or not at a given temperature. That's thermodynamics. Is it favored or not favored? Okay. The speed of a reaction is kinetics, and that's what we'll get into Unit 7. Okay, so kinetics studies how fast a reaction kind of happens or maybe gets to equilibrium, but thermodynamics doesn't tell you how fast it's going to get there. It's just going to tell you, yeah, it will happen eventually or it won't, but it doesn't tell you how fast. Okay. All right. A reaction has both negative enthalpy change and entropy change. All right, negative, negative. Okay, so it is found that delta G is 0 at this temperature. So that's the temperature tipping point. But a negative, negative, a negative delta H and a negative delta S, exothermic reactions become more favored as temperature decreases. Okay, so the reaction is not going to be thermodynamically above 250. So anything above 250, delta G is going to end up being positive, and anything below 250, delta G is going to end up being negative. And 250 is the temperature tipping point. Okay, so every reaction, if we go back to this chart, every reaction has a temperature tipping point. Okay, where it goes from spontaneous to non-spontaneous, and that's so. If you want to know what temperature is the temperature tipping point for a reaction, then plug in 0 for delta G and solve for the temperature. Okay, so in this example, where am I going? In this example, 250 was the temperature tipping point. Okay. And because we have a negative-negative combo, then we know anything below that temperature is going to be thermodynamically favored. Anything above that temperature is not going to be favored. If it was the other way around, if it was positive-positive, and we knew the temperature tipping point, for a positive-positive combo, anything above that temperature would be spontaneous or thermodynamically favored. Anything below would not be thermodynamically favored. Okay, but because this was negative-negative, we know above that temperature, not thermodynamically favored, delta G will be positive. Below that temperature, delta G would end up being negative. Okay, and at that temperature, that's where delta G equals 0. That's why it's called the temperature tipping point. All right, so I'm going to stop this video here. Go to part 2. Go to part 2 for the rest of this assessment.